Hello everybody, welcome to our discussion on the algorithm design course, and today we begin our lecture on the data structure heap sort and the various issues associated with it. Our common first slide. In the overall 6 steps of algorithm design, the design of data structures is a critical aspect. And we have seen several examples where these data structures are typically designed to ensure that the past computation is remembered in an effective and efficient manner so that it can be reused in the future to reduce our computational complexity. It typically comes with an additional space overhead, and because it comes with a space overhead, it also helps in reducing the time in most of the cases. In general, these data structures become common for a class of algorithms, and over a period of time, we have these series of data structures which can be used effectively for different kinds of problems. Among these data structures, today we will understand and study the heap data structure and the related data structures that we have been seeing in this course. So if we look back at the various kinds of problems that we have been solving, these include problems of searching an element, problems of sorting a set of elements. Then there are problems where we wanted to find the max, the min, the max and min, max and next max. Then in the second series of problems that we tried to solve, we ended up with the generalized recurrences, of which we saw the Fibonacci type of recurrences, or which I always call the Pingala or the Matra Meru type of recurrences. And we saw that here again we wanted to remember elements. Then we came on to solving a large set of matching problems. We saw pattern matching, we saw sequence alignment, we saw a large class of divide and conquer, greedy and dynamic programming problems, where in addition to the sorting problems that we have seen, we saw problems like the convex hull problem. We saw problems like the closest pair of points. We saw problems like matrix multiplication. Or we saw multiplication of n-bit numbers. And then we saw a large set of optimization problems, where we saw our famous coin selection problem. We saw in the class test, we saw the power line optimization problem. Power line optimal layout. Then we have seen the activity selection problem, We have seen the matrix chain problem, and so on and so forth. And in each of these cases, when we went back after having explored the first 3 steps of algorithm design, we ended up in the need for data structures. And the operations that we wanted to do, the data storage, memoization, access, and reuse. These were our fundamental things that we wanted in our data structures, where we would store these elements, and the various operations that were needed in these data structures. These included insert, delete, find. These were the fundamental operations. In addition to that, we had max, min. In case the key elements could be ordered by some ordering quantity, then we wanted to find the maximum, the minimum. Then we will see that there are several other operations that we wanted to do, including update key. Then we wanted to retrieve in ordered fashion, etc. And in order to do this, there are several kinds of data structures that are important, and we have been studying, of which in the first category are obviously lists, queues, stacks, arrays, etc. The second category were of the type of trees, and here we have discussed various kinds of trees and tree-like structures. If you remember, we discussed the tournament. We made a brief mention of a heap. Then in the max and min problem, though we did not discuss the heap in details. Then we made mentions of search trees, and we have started discussing binary search trees. And later on, we will again discuss more important data structures like graphs. There are other advanced data structures, but we will not discuss many of them here, but we will discuss several other data structures. Among the other operations that are important in these things include set operations. Because in many cases, we want to maintain a set. So here we want union, intersection, set difference, etc. And these will also form a various kinds. So graphs and 4 will be sets. So today in this lecture, we shall be discussing an important data structure called the heap data structure. We have made a mention of the heap data structure when we solved the max and min, the max and second max, and the sorting problems. So here we made a mention of these earlier. So how do we define a heap? A heap data structure consists of two properties. One, it is a complete binary tree, and secondly, it has what is called the heap property. When we say it is a complete binary tree, we mean that every node at all levels except the last level nodes, and that too the end nodes at the last level, always have two children. That means if this is a binary tree, then this is a complete binary tree, even though this node does not have a last child. So this is a binary tree, complete binary tree. On the other hand, if we list something like this, this is not a complete binary tree, because firstly, the nodes at the upper levels do not have both children, so that is why it is not a complete binary tree. The second is the heap property. The heap property states that for any node, so what is the heap property? The heap property says at any point in time, if you have two children, or in some cases you may have one child, then if this node has a value x, this node has a value y, and this node has a value z, then x must be greater than equal to y, and x must be greater than equal to z. Here I am talking about what is called a max heap. A max heap, there is an alternative min heap. In a min heap, these conditions will be reversed. That means x will be less than equal to y and x will be less than equal to z. So here in this case, if this is p and this is q, then here p must be greater than equal to q in a max heap. So suppose we have a heap structure as defined here. Suppose we have this, and we put in the values of the heap nodes, and we put in values 12, 3, 9, 8, 1, 2, then this satisfies the heap property at all the nodes, because 12 is greater than both 3 and 9, 3 is greater than 2 and 1, 9 is greater than 8. So this satisfies the heap property at all the nodes. On the other hand, if we had drawn it up like this, and we had made this as 7, this as 8, this as 6, this as 9, this as 2, this as 3, then the heap property is satisfied here, because 8 is greater than both 2 and 3, but the heap property is not satisfied here because 8 is greater than 7, and the heap property is not satisfied here. So this is how the heap is defined. The advantage of a heap is its implementation and its representation. We shall see that now. So the advantage of a heap is that the heap can now be implemented by a binary. This complete binary tree can be implemented by a simple array. Let us take an example. Suppose I have a heap like this. and the values of the heap are 19, 12, 16, 1, 4 and 7. Now there are these 6 nodes here, so I can use an array, and I can have the cells of an array. So 1, 2, 3, 4. Suppose I take an array like this. Then how do I store this? Because this satisfies the heap property at every node. So what I do is I number this in terms of the array like this. This is the first element, this is the second, this is the third, this is the fourth, this is the fifth, and this is the sixth. Which means that I have stored the elements of the heap 19, then 12, 16, 1, 4 and 7. And if I store these elements of the heap, then it becomes very easy to see how to access the heap. Now, if I want the left child of this node, so the left child left of any node n can be obtained from this array A at 2n location, provided this 2n is less than equal to the size of the array, a size of the heap. So there is also a size of the heap, and this is obtained at this, and the right child of any node at location n is obtained as A of 2n plus 1. As you can see, for the root node, which is at location 1, it is at 2 and 3. Then for the one which is node whose value is 16 at location 3, then its left child is at 6, but there is no right child. Similarly, because the size of the heap is 6 elements, and so 2n plus 1, the 7th element, does not exist. The other very interesting thing is the parent. A parent of n can be obtained from A n by 2 float. Suppose I want the parent of the node number at index 5, whose value is 4, then 5 by 2, the floor of that is index 2, and therefore the parent is the node 2, whose value is 12. So by this simple representation and very compact representation of the heap, we are able to obtain all the properties of the heap. And therefore, given a heap, we will have the following functions on the heap. One is size of heap. If A is the heap, you will get size of. Then you will have left child of the heap A given a node n. You have right child A given a node n, and you have parent of A given a node n. Then in addition, you also have the root of the heap, which is A1, and you have the end of the heap, which is A size of A. So based on these simple properties, and these straightforward manipulations of a heap, which is represented by a simple 1D array, we will be able to get the next elements of the heap. So now, once we have seen this simple array-like representation of the heap, we now move on to the heap operations. So in a heap does not have all the operations that we want from a data structure. The primary operations that we want on a heap are as follows. The primary operations on a heap may be of two types, a max heap or a min heap, because it will be either ordered in the max ordering or in the min ordering. So the first operation is the insert new operation. That means we will insert a new element into the heap. And the function of this insert operation is that after you maintain, so you will insert, this will insert a new element, and reorder the heap to maintain the heap property. So if I have to insert an element whose key value is k, it will insert this new element with key value k. So this will insert an element with key equal to k and maintain the heap operation. That means the heap was having a heap property, it will now maintain the heap property. The next is remove max, it being a max heap. So this will remove the largest element from the heap and reorder the heap to maintain the heap property. In the case of a min heap, it will do the opposite. This is for a max heap. This is for a max heap. As we have seen earlier, that the max element of a max heap is always at the root. So the objective is to remove this element and then reorder the heap so that the heap property, which is mentioned here as the heap property, this heap property is maintained and it continues to remain a complete binary tree. The third important operation in a heap is build heap. That means this, given a set of elements, make a heap which satisfies the heap property. These are the three primary operations. There are a few auxiliary operations, and these auxiliary operations on a heap include which are there, but they can be used only if the node element of the heap is made available. So one of them is update the key value. So it will change the key value of the heap and then reorder the heap and maintain the given. So this will given a heap A and a node N, given a heap A and a node N and a key value K, so given a new key value K to a node N, it will update the key value and reorder the heap to maintain heap property. The other operation is delete, where given a heap and given the index to a node, you will delete the element and maintain the heap property. The difficult operation is the find. The heap is not designed to, the find operation says given a key value, find that node in the heap which has the key value k. This is a difficult operation for a heap and is not considered for a heap. So the primary operations are insert, remove max and build heap, and the update key is available provided you have the access to the node and you don't have to use the find operation. Similarly, the delete key operation. Now we will see each of these operations one by one. So let us look at our example of how we will insert a new element. So suppose we have a heap like this. Which was 19, 12, 16, 1, 4, 7, and as we said, we maintained it as an array. One, two, three, 4, 5, 6, 7, 8, 9, let us say, and the values will be 19, 12. This is the representation of the heap, 16, 1, 4, 7. Now, suppose we are told, so here we know we are told to insert a value, let us say 17. So, in order to insert 17, what it will do is it will go to the end of the queue, which is the last element is 6. So, it will go to increment 6 and add this 17 here, which means that it is adding 17 here. Once it adds this 17 here, then it will have to add 17 at end, and then the most important operation is propagate or update upwards. So how will it do an update upwards? It will now go look at the parent and it will compare and check whether this set satisfies the heap property. That means whether the parent satisfies the heap property or not. And here you notice that since the parent does not satisfy the heap property, it will exchange node and parent. And therefore this will become 17 and this will become 16. After it has updated this, it will then check, because of this new node insertion, the only this value, if it was something else, it wouldn't have been a problem. On the other hand, now after it has seen 17 and this has been updated, it has to again check here. Now checking with 19, it finds that this is fine. So it will stop here. Let us see another example. Suppose this was 19, 12. So after this, this has become 17, this has become 1, this has become 4, this has become 7, this has become 16, and now I want to do insert. Now I want to insert, let us say, 23. So the question is, where will I insert 23? Now, as soon as I put in a new node, as you can see, this new node 23 will go into location. So this is location 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So already we have got 19, 12, 17, 1, 4, 7, 19, 12, 17, 1, 4, 7, 16. And now this new node 23 will be inserted here. As per our rule, who is the parent of 23? Who is the parent of node n equal to node at 8? The parent of this is the node equal to, this node will be 8 by 2 will be 4. Will be node number 4, which is here. If our nodes are numbered, this is node 1, 2, 3, 4, 5, 6, 7. And the 8th node here will now be inserted here, 23. This is how it is inserted to ensure that the complete binary tree happens. Now this is a complete binary tree, but it does not satisfy heap property. So this will be exchanged, this will become 23, this will become 1. Again 23 will go up here, this will become 12. Again 23 will go up here, and this will become 19. So by this, we will have the insertion of a new element into the heap. So having looked at this insertion, we now see how we will be applying this insertion. So the insertion step, as we said, consists of two parts: add a new element to the end of the heap, and the indexing of the heap ensures that we know who is the parent and we know exactly where it is inserted. So we add the element and percolate or update the cost upwards. So now we come to the algorithm for insertion. So our algorithm insert an element a new element k into the heap. This will be adding to the heap an element k. So this adds to end of a and then calls update the cost of the heap upwards, and once I add this, I will get a node n. I will get the access to the node n, and I will update this cost up. As soon as I add a node n, I will add a node n, I will add this at the end of the heap, get a pointer n, which is the index of that array, and update it upwards. So how does the update up algorithm work now? We have seen how it works. If node not equal to, if the node is not equal to root, what is the root? The root is A1. If the node is not equal to the root, then we check if the node's key, the key value of this node, is greater than the key value of the parent. So we check if the key of node is greater than key of parent of node, sorry, we have to write an if here. If the key value of the node is greater than the key of the parent of the node, then we have to exchange. So we have to exchange node and parent, and then we have to again propagate upwards and check upward. If that is not the case, if this is not the case, then the algorithm terminates. Otherwise, we have to again call it update up A of the parent. This is how we saw the algorithm, and this complexity. What is the complexity of this algorithm? The complexity of the algorithm, in each step there is one step, so the complexity of the algorithm is the height of the heap in the form of a binary tree. And it is obvious that since the heap is a complete binary tree, where every node other than the last few nodes at the last level have both the children, this is very clear. If the heap has got n nodes, it is log n. So the complexity of this insertion operation is log n. So adding a new node into a heap with a new key value will be of complexity log n. The next operation is the remove max. We know that for a heap, the root, so the max element lies at the root for a max heap. So as in our case and in our example which we had, this was 19, 12, 16, 1, 4, 7. So now the max element lies at the root, and in order to remove this max element, what we will do are 2 steps. Our 2 steps are: 1, remove the root, which is the same as A1. Replace A1 by A of the size of the heap A, and reduce size A by 1, which means that in this particular case I will remove 19, will be removed. This 7, which is the last element here, will come and replace this. The size of the heap, so this will become 7. The size of the heap, sorry, this was the size of the heap. The size of the heap will now get reduced to this. But this does not have the heap property. So now we have to update the heap property. But this updation is no longer an updation from the bottom to the top, but an updation from the top to the bottom. So this will be an update down A node. This node here in this case will be the root. But in general we can update down any value. This update down function in our algorithmic parlance is also called the Heapify A node function. This is nothing but the update down function. So how does this update down work? Now that we have this, the update down works in a very straightforward manner. Just like the update up compares the parent, the update down compares the 2 children. And if the node at the root here is less than the larger of the 2 children, it exchanges it with the larger of the 2. Which means in this case, this will become 7 and this will become 16. So here, after the operation is over, this will become 16, this will become 12, this will become 7, then 1, then 4. And it still maintains the heap property. So now, like we did the update up, now we will do the update down, which is called the Heapify function. The update down function is very similar to the update up function, and this Heapify function is the straightforward function, again a recursive function like we have seen before. So now we look at this Heapify function. So how does the Heapify function look like? Heapify function, or the update down function, is update down A node it will let L be the left node, left child, let R, sorry, this as we had defined this as left child, huh? We had defined our left child, right child. So fine. So this is the left child, This is the right child of the node. I am not giving the array index here or the heap number here, but it's obvious from the node I will be able to get it by the straightforward array operations that we have defined. Then we find the larger of these. So the larger of these, so if we have to write the larger, is the largest node is the one with the largest key value among node L and R. So this node is the largest among its L, R. If this largest node among all of these three, if the largest node is the node itself, then there is nothing to do because that the heap property is maintained. So if large is not equal to node, then again I will exchange. So I will again exchange node and large as we have seen, and I will again call this update down. So this one updates it downwards, and this update down, as we have seen in our previous example, we had this sort of an example and we created this new array. Let us see if we want to delete an element from this now. So we had ended up creating 16, 12, 7, 1, 4. This is what we had done after this step. At this step, after this step, we had done this. So this would have become this would be 16, 12, 7, 1, 4. Now if I apply remove max on this, then what will happen? As per our method, this will get removed, 16 will go here, 16 will come out, and which is the last element? Here. This last element will replace 16. So this 4 will get removed and 4 will come here. And after 4 comes here, the size will now get reduced to this size. And as soon as 4 comes here, then the update downwards program will continue. So the larger of 12 and 7 is 12. So 12 will go up here, 4 will come here. And after all this is done, the revised new heap will have 12, 4, 7, 1. This will be the updated heap. Now what is the complexity of this? Again, it is the height of the heap. Which is again order of log of n. So both our operations, insert and remove max, are having a basic property of it being maintaining the heap property, or both are of order log n capacity. Now we will see how to build the initial heap. So to build the initial heap, what we do is a very simple thing. We have two options. One option is to insert element one after another. So option 1, insert the n elements one after another. But this will take order of n log n time, because each insertion is of the order of log n, and we go on insert. But we will apply the option 2, which does the following. It stores, so option 2, which is the build heap, this option 2, what it does is it store initialize a randomly. That means whatever are the inputs as per input. So whatever is A is given as per input. Now what I do is as follows. Suppose I have a heap like this. Suppose I have a heap like this. And here are my elements. So this is my array index, and suppose my elements are 6, 8, 4, 12, 1, 9, 3. So which means that my elements are stored in the array 6, 8, 4, 12, 1, 9, 3. This is how it is initially given. Now I start from half the point. That means first I will, so the order of heapification, I will first update this node. That means I will update this node 4. Then, so I will update this node 4 first, then I will update this node, then I will update this node. Which means I don't need to update the leaf nodes, but I will update the intermediate nodes in the reverse order of its existence. So what I will do is first I will update 4, this node. As soon as I update this node, what happens? This node, by applying that update down function, it will only look at this level, and by looking at this level, it will update this, and this will become 9, and this will become 4. Then I will update this node. Looking at this, this will become 12, and this will become 8. Now I will update this node. Looking at these two, this will become 12, and this will become 6. And the Heapify algorithm will continue, because this is being done, this will be done. Then this will become 8, and this will become 6. And finally, after all this is done, my array or my heap will now have 12, 8, 9, 6, 1, 4, 3. So now we can write down the algorithm. The algorithm, what it will do is it will do a for loop for I equal to array A size by 2 to 1. That means I will start from, if there are 7 elements, I will start from 3, then I will do 2, then I will do index 1. So the indices here are, this is index 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So I will start from size half the root, the parent of the last element. I will start from the parent of the last element, which is the node number 7. Its parent will be 3 by the definition, and then I will do node 2, node index 2, then I will do node index 1. So I will do this, and I will simply do the following. I will run my update down AI. So I will iteratively do an update down AI, and it is easy to see that this algorithm will have, it is easy to see that this algorithm will be of order n complexity. Why? Because at every level, this level which is at the level of level 2, which if we look at it from below, then the leaves are at level 0, those at level 1 will see height 1. There are n by 2 elements who will do height 1, n by 4 elements height 2, n by 8 elements height 3, and so on and so forth, 3 levels down. So I leave it to you to figure out why this is order n. It's a very simple calculation. So this algorithm of building a heap will make it easier to build the heap, and it will be a faster algorithm than inserting elements one after another. Now, having done these 3 operations, build heap, insert a new element, and heapify or remove max, with these 3 operations, I am now ready to do heap sort. So how do I proceed with heap sort? So my heap sort algorithm first does a build heap A. So I will first build the heap, and then one by one I will remove the element as the root, which is the root, put it at the end of the array, and then continue. So let us look at our example. Suppose my example is like this. So this is 20, this is 16, this is 14, this is 3, this is 8, this is 9, this is 1. So I have, this is after build heap. This is after build heap. After I have done build heap, I have got this. The next step that I will do is I will one by one swap. So I will do this operation. Swap A1 with AI. This A1 is the root. So I will swap A1 with AI. A1 is the root. AI is the last element. So I will one by one swap A1 with AI. So what will I do here? I will take this, swap it like this. So this will become 20, this will become 1. So this will become 1, and this will become 20. So as soon as I do this, I will reduce the size of the heap because I have removed this element. So I will now reduce the size. Size is equal to size minus 1. And now that I have put 1 here, this element here, I will have to update downwards. That means I will have to call update down A1. So I will again call update down A1, and as soon as I do that, this value will become initially in the first round 16, and this one will go down and become 8, and this will become 1. Now I have got my heap up to here, and my largest element is here. Now I repeat the whole process. Now I will remove 16, replace it, swap it with 8, with 9, with the last element, and again apply this in decrement size and apply this. And I will go on doing this till I do it till the second element. The last element is not required. So this for loop that I will now write is for I equal to size to do, and I will do these steps. So now once I have done this, and I have obtained, after doing this, my heap property is maintained like this. 20 is at the last value, and this, after the first round iteration is done, this becomes 16, this becomes 8, this is 14, this is 3, this is 1, this is 9. And in the next round, 16 will be replaced by 9, and the heap property will continue. And as we can see that this will continue going. And so just if we continue this example, then we will have our nodes as follows: 16, our 20 is here, our 20 is here, and we have seen 16, 8, 14. This will be 3, 1, 9. So this will be 16, 8, 14, 3, 1, 9, and the size is here. Now once this happens, immediately the next step will be as follows. This 16 will come here, 9 will come here, so 16 and 9 will get exchanged. Size will reduce by 1, and as soon as size reduces by 1, the update cost will be applied, and as soon as update cost is applied, this will become 14, this will become 9. And this will not get updated because the size now has reduced to 5 elements. 1, 2, 3, 4, 5 elements. So this part is outside the boundary of the heap which is happening. So as soon as that happens, the heap structure will now become this will become 14, This is 8, this is 9, this is 3, this is 1, this is 16, this is 20, and the size is here. So my heap structure after this has become 16, 20. These two are outside the heap, and I have 14, I have 8, I have 9, I have 3, and I have 1. And now the next step, as per the iteration, this 14 and 1 will get exchanged. And as soon as 14 and 1 get exchanged, this will become 1, this will become 14, this will now become part of the outside of the heap, and then this will percolate between these two. This will become 9, this will become 1. So after this operation is done, we will have we will have 9, 8, 1, 3. This is the size. Size will be here now, and we'll have 14, 16, and 20, and this is the original size. This is the original size. And as you can see, sequentially, in every step, this will reduce. So the analysis of heap sort is very simple now. If we look at the algorithm, build heap is order n, and sorting, this consists of remove and exchange. This is order 1, and then is update down, which is order log n, and this is done order n times. So therefore the heap sort is an order log n. So heap sort is an order n log n algorithm, and compared, I'll leave it to you to compare with. It's very tricky but very interesting to compare with quick sort, merge sort, and compare here means both space and time and other sorts. And among them, heap sort is a very interesting sorting algorithm because of its typical manner in which it represents in a very compact form a complete binary tree, which is not a binary search tree, but it maintains a special property called a heap property. So there are several extensions. So we have not yet discussed several other operations like the update, cost, delete. I leave it to you to think about how we'll be updating and how we will be deleting. In general, other than sorting, we may have a dynamic series of data structure operations which involve insert, remove max, insert. So you can have continuously a series of alternative operations in some cases. Heap sort is only one way to operate this heap data structure, but this heap data structure could be operated in multiple other ways, and there are several extensions that we want, several new operations that we want, and we shall study all this in the subsequent cycle, in the subsequent lecture, and we shall see how we can implement a very important data structure called a priority queue with a heap, and see how it can be applied to various other operations. With this, we come to an end of this lecture. Please feel free to